What we're going to do here is we're going to take an equation of a linear non-proportional relationship. We're going to create a table, and then we're going to use that table to actually graph the relationship. So I've cheated a little bit here, and I went and created the blank graph beforehand so that I wouldn't have to spend time drawing it. But we're going to do everything else from scratch. We're going to take the equation, create the table, create the graph. So let's go ahead and read our problem. It says the diameter of a Douglas fir tree is currently 10 inches when measured at chest height. Over the next 50 years, the diameter is expected to increase by an average growth rate of 2/5 of an inch per year. The equation is y equals 2/5 x plus 10. Um, the equation y equals 2/5 x plus 10 gives y the diameter of the tree in inches after x years. Draw a graph of the equation, describe the relationship. So to draw a graph, we need a table, and we're told here in this second to last sentence that the equation gives us the diameter y in terms of x years. So whenever we create our table, which is where we're going to start, we've got x, which is years, and y, which is inches. We want to pick values for our table that are going to make sense. So we don't want to pick negative numbers. Might be okay in this case for us to use 0, since we know that it is currently 10 inches tall, meaning when we start, the tree is 10 inches tall. So I think 0 is actually a pretty good point to use. That'll give us the y-intercept of this graph, which will be useful. And then you may be tempted to just use years 1, 2, 3, 4, 5. And that's fine. Using 1, 2, 3, 4, 5 is fine. But what I notice about the equation, y equals 2/5 x plus 10, is that using 2/5 is a pretty unfortunate number to have to multiply by. Doing 2/5 times a number is going to give us a fraction or a decimal answer most of the time. So what I want to make sure I do so that I avoid dealing with a lot of fractions and decimals is I want to multiply by something that's going to make sure that when I do 2/5 times that number, I end up with a whole number. So what can I multiply 2/5 by that will make sure my answer is a whole number? Since the denominator of 2/5 is a 5, what I know is that if I multiply 2/5 by a multiple of 5 or 10, I will come out with a whole number. So for example, if I do 2/5 times 5, 2/5 times 10, times 15, 20, 25, anything that is a multiple of 5, it's going to come out to be a whole number. Well, this problem says that I'm measuring this tree over the next 50 years. So why don't I just go from 0 to 50? And if I'm going from 0 to 50 and I want multiples of 5, why not just go 10, 20, 30, 40, 50? I could do more than that if I really wanted to. I could do, 5, 10, 15, 20, 25, 30 like that. But that seems excessive to do that many points. So let's just go by tens. Going by tens actually is probably too many points, but this is okay. So we're going to go by tens. So what we're going to do is take each one of these points, 10, 20, 30, 40, 50, and plug them into our equation here. Y equals 2/5 x plus 10. Okay, so we're going to do y equals 2/5 x plus 10. And then we're going to take each one of these values we have chosen for x, 10, 20, 30, 40, 50, and substitute them for x in the equation and see what's y. Okay, so let's start off with 10. So we do 2/5 multiplied by 10. So if you're not super good with multiplying by fractions, totally fine to use a calculator to do 2/5 times 10. The way that you do this, if you're going to try to do it without a calculator, is pretty simple. Multiplying a fraction by a whole number, you multiply the numerator by the whole number. So you do 2 times 10, which is 20. 2 times 10 is 20. And then you divide by 5. So 2 times 20, or sorry, 2 times 10 is 20, divided by 5. 20 divided by 5 is 4. So 2/5 times 10 is 4, and 4 plus 10 is 14. So in 10 years, this tree will be 14 inches tall. Boy, it's a good thing people don't grow at that rate. Can you imagine if you only grew 4 inches in 10 years? That would be unfortunate. All right, let's try 20. 20 plus 10. Okay, again, you can use the calculator. You can do 2/5 times 20, but this is the same thing as 2 times 20, which is 40, and 40 divided by 5 is 8. So 8 plus 10 is 18. And boy, I am noticing a pattern. 10 plus 4 was 14. 14 plus 4 is 18. Let's go ahead and do it one more time just to see if the pattern holds true. Let's do 30. 2/5 times 30. My prediction is that this is going to be 22. What do you think? Think we're going to get 22? So 2 times 30 is 60, and 60 divided by 5 is 12. So this is going to be 12 plus 10, and hey, what do you know? It's 22. So look, we see a pattern here. Plus 4, plus 4, plus 4. Looks like every 10 years, this tree is growing 4 inches. So we don't need to do the equation anymore. Every 10 years, we're going up 4 inches. So that means we're going to have 26 inches after 40 years and 30 inches after 50 years. Okay, great. So we've got our table, we've got our points. Now the next thing that we need to do is we need to graph our equation. Okay, great. So our x is going from 0 to 50. So we need to make sure we label our x-axis from 0 to 50. And our y is going from, it's going from 10 to 30, but we're going to start at 0, just so we've got that origin there in our graph. So our y needs to go from at least 0 to 30. Okay, so let's go to our graph here. And let's see, we've got a whole bunch of lines here on the bottom. Let's see what we need to go by here. I'm thinking we can probably, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 21, 5, 6, 7, 8, 29, 30. Okay, we've got 30 lines here on the bottom. 30 lines. And that means if we make every line worth 2, if we go by 2s, we can get all the way up to 60 here. So let's do that. Let's go by 2s. Now I'm not going to label every one of these, of course, because that would take forever. So let's just go 2, 4, 6, 8, 10, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48, 50, 52, 54, 56, 58, 60. There we go. It goes all the way to 60. And hey, that works out well since all of our x's are multiples of 10. Should be really easy to find those points. Okay, let's go ahead and look at the y-axis now. And the y-axis needs to go at least from 0 to 30. So let's see how many lines we've got on the y-axis. Let's go ahead and count real quick. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 18, 5, 6, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36 lines. That is helpful. 36 lines. And we only need to go to 30, so that means we can just go by 1s. Well, that's nice. Let's actually just measure by, let's say, maybe 5s. 1, 2, 3, 4, 5, 6, 7. The x and y axis do not have to go by the same amount. So it's fine for us to have one going by one amount and one going by a different amount. Totally fine. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There we go. Okay. So x-axis goes to 60, y-axis goes to 36, which is great because that's what we needed to show, at least that high. Let's go ahead and plot our points. So the first point that we had on our table is 0, 60. Let's go ahead and do a really bright red color here so it's easy to see. So let's do 0, 10. Did I say 0, 60 just now? I meant 0, 10. 0, 10 was our y-intercept. Our next point is 10, 14. So 10, 14 is right here. Those are actually the only 2 points I need to put because since this is linear, I can get away with just 2 points and draw a straight line. But we went through all the trouble of making this big long table. I say we go ahead and take advantage and do all of our points. It's always best to use all the information that we have just to be as accurate as possible. Why go through all the trouble of finding all those beautiful, beautiful points and then not using them? That would be such a shame. There's one thing we don't want to do, it's waste math. There we go. And I feel pretty confident that we've done this correctly because all of our points are in a straight line. So if I take my ruler and I put my ruler up against these points, they should all line up perfectly. And hey, what do you know? They do. So let's go ahead and do our line all the way across. And what we're going to do is we're going to put our line here and we're going to put an arrow on the end of our line to show that this tree could keep growing, probably will keep growing. We didn't plot any more points. We don't know that it grows at the same rate, but probably this tree is going to keep growing. So we'll put an arrow on the end to say, etc. The tree's going to probably keep getting bigger, but that's where we're stopping our data. So there we go. We took an equation that was non-proportional but linear. We used the equation to create a table, and then we used the table to create a graph.